10.3 is just comparing our exponential graphs with our linear graphs. So we're just going to go ahead and dive right in because this is review. So it says, Scenario 1. A zombie virus has been discovered in Valparaiso. The virus has infected one person so far, Mrs. Taylor, but she's infected 2 new people each day. The new people do not infect anyone new, only Mrs. Taylor can do it. So we're going to fill in the table to show how many people have been infected by day 30. And I started it for you. So on day 1, she infects 2 people. On day 2, she has 2 more, which makes it 4. Day 3, she infects 2 more. So this is all increasing by 2 because she is the only one that can infect new people. So I'm just going to add 2 to all of these for my table. So by day 30, she's only infected 60 people because she, again, just is doing 2 people each day. Scenario 2 says Mrs. Stanfield has also been infected, but by a different strain of the zombie virus. And when I infect 2 people, those 2 people infect 2 more, who then infect 2 more, and so on and so forth. So my strain is much more contagious. We're going to fill out my table now. So on day 1, I infect 2 people. Then those 2 people infect 2 more people. And then we have 4 people, and then all 4 of those people infect more people. And then we infect even more people at a rate of a very fast pace, as you guys can see. It is doubling by 2 because we are all infecting people. We are all contagious. And so these numbers are growing, as some would say, exponentially because they're getting very large very fast, and they are doubling. Oh man, I should have had some of this table filled out. 768. So just putting this in my calculator, which I already did before I started the notes, to figure out what every one of these is doubled. 576. No, it's at 2,000,097 152. It's at 4 million. So just me infecting those few people, the fact that they were able to infect more people is making the zombie strain clearly grow out of hand. Now I'm at 16 million. I'm not even done yet. So day 25. Zoom in a lot so we can see 33554,432, and that doubles to 67,108,864, then 134,217. Ooh, I think that's a 228. I hope that math was right. 268. 435, 546, and we're at 536,870,912. And lastly, by day 30, I would have infected 1 billion and some odd change. So if you graph both of these situations, we should see a relationship, whether it's exponential or linear. So for number 1, the days is your x column. And our y value is the number of people infected. For doing the first one, that one is really easy to see. I'm just going to go by 2's on my x value. Um, 12, 14, 16, 18, that would be 20 right here. And that's 30. So I just went by 2's. And then, let's see, I'll have a break here. And I'll start at, I don't know, 9 and go up by 6's. Hopefully I have enough room. 51, 57, and then I might have a little loner up there at 60. So when I graph this, I should have a pretty straight line unless I did not number that correctly. So if I go up to my first scenario, on day 1 there were 2 zombies. So that's somewhere hanging out over here. Day 2 there were 4. Let's go down to when I can actually get on my graph here. Day 4 there were 8. Day 5 there were 10. Gosh darn it. I cannot get a dot on the graph. Okay. Day 6 there were 12. Day 7 there were 14. Day 20 looks like there were 40. You guys need to fill out the rest of the points on your own. I'm trying to save time here, especially because I can't get a dot on my iPad. On day 30 there were 60. But I think you guys are starting to see, just based off of the 1, 2, 3, 4, like 5 points that I sketched in, this should be a line. So my situation in scenario 1 is a linear graph, because when you plot all of those points, we're going to have a line. And that was also made pretty clear by how it only increased by 2 every time. The next one is clearly growing exponentially because those numbers got ginormous. To graph this one would be incredibly difficult and take a long time, so we're just going to do a rough sketch here. We're going to say this is 1,000, 3,000, 5,000, I did a 6,000 on my key, but I guess I did 6,000, 8,000, 10, 12. It's really hard to write this on that good. 14, 16, 18, and then 28,000. So on this one, even if I write out my days, so I have 2 days, 6, 8, that's 10, that's 14, So let's just take it to oops, I did that wrong. That'll be at 22, 26, and then 30. So I'm not even going to get to 30 because those numbers grew so fast. But when we were at day 2, we only had infected 4 people, so clearly that's so low down here. It doesn't even really register. Same with day 6. Day 10, we were getting somewhere. Day 10, we were at 1,000. Day 14, we were up to 16,000. Day 14 we were up to 16,000. I did 1,600. And there is your exponential relationship because that just bloop, flew up there. So we're just comparing these two. So if I go down and answer the questions, it says if the population of Valparaiso is 28,794, on which day will the entire city be infected in scenario 1 with Mrs. Taylor? So, for Mrs. Taylor, if we have 28,794, and we're infecting only 2 people each day, that's going to happen. It's going to take forever. It's not going to happen until we basically split the population in half. For Mrs. Stanfill, we already did this. The day that we infected at least 28,000 was right around day 15. And that just came from my table. Okay, which type of function is represented in scenario 1? Scenario 1 made a line, so that's linear. And scenario 2 is exponential because it had rapid growth. We spread that virus really, really fast. So if there really was a zombie virus outbreak, which would give us the better chance of surviving? Clearly that would be scenario 1. And that's linear. Oh shoot, I only have 2 minutes. Alright, so you guys can refer to this stuff as your notes, but basically linear functions is mx plus b, exponential is a bx, and there are some graphs to show you that. The relationship that's important here is looking at your y values and what's going on. If it's just adding or subtracting, it's linear. If it's growing or decreasing rapidly, it's exponential. So determine which of the following. So for number 1, that is an mx plus b form, so that is linear. The next one has an exponent, so that is exponential. 3 has a radical, so that is neither. You guys don't know this yet, but if it has the squared, it is neither, because it has to have an exponent of x. 5th power again, neither. This has the x and the squared. Again, it's neither. This is something that was on our e-learning. That is exponential. And this is a linear graph because there is no exponent of x. Looking at 9, you would just plot these points and determine which one is linear and which one is exponential. So if you were to plot, you guys are going to do 9. If I were to do 10, negative 9, 1, negative 6, negative 1, negative 3, negative 3, oops, wrong one, negative 3, negative 3, 0, negative 5, that made a line, so this one is linear. And then looking at the tables here, we're looking at our relationships, so we're looking at your y values. For these y values, it's being added by 2, and that is constant. It's happening the same. is linear, because you're adding 2. And then the next situation, y is being 1/3 to get to 1. You're timesing by 3. From 1 to get the 3, you're multiplying by 3 every time. So that is exponential. So it's growing really fast. And then lastly, we are decreasing by 6, decreasing by 2, adding 2, adding 6. There's no pattern, so there's no relationship.